last talk, first lecture, geometric approach to water waves and the free surface flow.
Thank you. Yes, so it is good that we just had this lecture by Professor Garofalo, because I will be using very similar ideas in the. So I think that for the students, some sort of conclusion is that when you study singularities in free boundaries or regularity and so on, so these blow-up techniques are really, well, the most natural tool. And if you have some monotonicity formulas or frequency formulas, those are of great help in order to identify unique blow-up limits and deriving the conclusions that you want. So let me recall the problem that we are studying. So so it is here, this divergence form elliptic operator with singular weight at the axis. So okay, we have the picture here with this nonlinear boundary conditions and so on, and the solution, the notional solution that we consider is this one. So some sort of weak formulation involving test functions phi. Okay, and so we said last time that at each points on the free boundary, we can exhibit some monotone quantities, and but today, so I will just concentrate at the origin. So here the equation has is scaling invariant with exponent 5/2. So we consider this blow-up sequences and so on, and we have a relevant monotonicity formula. So so which consists of the energy of the problem rescaled in a certain way, and the L2 norm of the function on the boundary of the half ball, again rescaled in the right way, and then we have this monotone quantity, and so this function is monotone and has a limit at 0. And this is helping us to prove that, so if we take this kind of blow-up limits with exponent 5/2, they converge to function u0, which is homogeneous of degree 5/2, and we had a classification of all possible solutions with such homogeneity, but one of them is u0 identically 0. So so in what follows, I will concentrate on the case where this happens. Yes, so so doing this blow up, we have lost all the information on the problem, and this 0 limit is for the blow up is associated to a certain, well, in fact, to two different values of the limits of the monotonicity function, and so I will look in what follows at the case. So we had a full classification and so on with all possible values. So we have convergence to 0, and the values of the limits are okay, one of these 3 and so on, but I will look at this one. So what is this telling us? That in the limit, the water phase occupies the upper half plane. So this is yeah, so if you look at this definition, so x2 plus, so so we are dealing with the situation where the free boundary, so Okay, this is water, but recall that we have reflected the problem. So in the physical plane, so water will be below air, and we have a very flat point here, so that the curve enters the origin horizontally, and then in the blow-up limit, so this horizontal curve will become a horizontal line, and here we have air. So so this is so we get this value for the limit of the monotonicity function. So it is this case that I want to consider in what follows. So okay, so exponent 5/2 led us to 0, but maybe if we take a different exponent, we can get a non-trivial limit, but then what should that be, and so on. And we don't know, and so the idea is to take a different kind of scaling, like in Professor Garofalo. So we normalize the function to make it of norm of L2 norm equals to 1 on the boundary. So namely, we are looking at this kind of thing. So u of Rx, so divided by the L2 norm on the boundary of the ball of radius R, always with this weight 1 over x1. So this is what makes all of our equations work nicely, because this weight is present both in the equation and the boundary condition. Yeah, so the question is, we want to look at the behavior of this sequence, of this family depending on R, which so we call VR, so to say. And the final result is that, so the assumptions are, so this is the value of the density at so this I said we call the density. So this is the density, the air region. So in the half plane we have air, so u is 0. And then for this rescaled sequence, this blow-up sequence, we are able to identify a unique blow-up limit. So this is the final conclusion of my analysis. Yes, please.
W notation, W1 to W?
So this refers to the weight on the, so we are looking at functions for which integral of gradient u square with this weight 1 over x1 is finite. So the notation means. Okay, so the conclusion is that there is a unique blow-up limit, which is, so this is just a constant, and this is homogeneous of degree 3, so to say. And as a further outcome of our analysis, so if you actually look at power, so if you do this rescalings with power, so if you take alpha smaller than 3, you get convergence to 0. And if you take it bigger than 3, this will grow unbounded. So this suggests that maybe if one takes alpha equals 3 here, we will get something like this. So this is some sort of conjecture, but we don't know. So so we only know that if we rescale in this way, we get this limit. But and then alpha different from 3 leads us either to 0 or to infinity. But alpha equals 3, we don't know what happens. Okay, so this is the final result that I would like to get. And the main tool is frequency formula. So okay, so here convergence is strong and so on is less important. So now it is okay. So I am indicating some. So this is the function that I want to study, for which I am claiming monotonicity, and but in my for my argument, it is important to know what is actually the derivative, and these are two different formulae for the derivatives. But so let us look at these terms. All of these terms again, which are involved. and compare them to those in usual Almgrens formula, or like in Professor Garofalo, so what he had. So you see, so there is a part here which is Dirichlet energy weighted, and then L2 norm on the boundary again weighted, so, and with R in front, so this is the natural thing. And then in the, but we also have a free boundary and positivity set and so on, and such terms also occur in our frequency function. So there is this thing which is occurs in the energy x1, x2 times the characteristic function, from which I am subtracting the density. So x1, x2 times 1 and so on is corresponds to the density. So if you look again at this formula here, so the part without 1 is the energy in my problem, and then on the bottom is the L2 norm on the boundary, and then with an R in front, and they are all weighted and so on. So in the 2D problem, we have exactly similar formulas, but without these weights and so on. So these are due to the axisymmetric nature of the problem. So yes, so we say let us look at this expression, and we have these two formulae for the derivative, which are closely related, but not exactly the same. And the idea is that all of these terms here in the right-hand side will turn out to be non-negative. So this is maybe main terms involving squares. Okay, so these are non-negative. And then, so D is Dirichlet. This is some sort of volume involving characteristic function. This H is the difference. So we have things like this and like this. And yes, so the conclusion that I would like is that H is monotone, and for that we need to say something about these terms here, and some results about that are given in this auxiliary result on this side. So take a solution of our problem and so on. Then this frequency function defined on the previous slides is always bigger than 5/2. Then this second line is not so relevant. Then the third bit is that this is monotone, has a limit, and the limit greater than 5/2. So this will follow because the function is greater than 5/2. And then there is this integrability condition, which is also important later on. So, but this is the really important thing. So why is the function always bigger than 5/2? So for that, we look again at the monotonicity function. So this was the definition. So it's this and this. And that was an increasing function with R, so this expression is greater than the limit at 0, which I have assumed to be this one. So now if I take this term, so look at this inequality, take this term and move it here together with this one. Yes, then this is sort of like Dirichlet part, and this is the L2 norm. So, and when you divide by this, you get that the ratio between this minus this and the L2 norm greater than 5/2. So it follows in a really easy way from the monotonicity formula that this H is greater or equal than 5/2 all the time. So now if I get back on the to the formula here, and use the fact that H is greater than 5/2, and V is, if you look at it, so it is always non-negative. So absolutely every term here is non-negative. So the derivative of this function h, which is, you can use either of those formula, is non-negative. So in this way we have exhibited a frequency formula, and the important thing here is that it is valid only at points of highest, well, so here there is no claim about monotonicity, but so this is generally valid, but the monotonicity is true only at points of highest density. So this is the key point. So if we didn't know that that we have a this kind of degenerate point of maximal density frequency, so this frequency function will not be monotone. So this is adequate, especially, well, only for the case that we really care about of degenerate points. So at all other points, one cannot write down a monotone expression of this type. Okay. So is there anything else that I could say here? Yes. So we have this monotone function, and I would, so the direction that I want to get is that this will give me homogeneity of the blow-up sequences. Yeah, so it is this kind of things. So so at the, maybe this factor shouldn't be here. So we now look for blow-up sequences like this. So do some rescaling and divide by L2 norm on the boundary. So first of all, these are bounded in Sobolev space W12 with the weight. Then a really important conclusion from the previous analysis is that so both of these functions d and v have a limit. So if you look at the formula, so h is the difference between d and v. So both of these are non-negative, as we can see. So it's the difference of two things which has a limit. But now we are saying much more, that each of them actually has a limit. And moreover, so this v part with characteristic function and so on goes to 0, and this d part goes to the limit of h. So this is the conclusion of the first line, and this is quite non-trivial, so to say. So it really requires careful analysis to draw a conclusion. So not only about the difference, which is monotone and has a limit, but about each term individually, that this goes to 0 and this has a full limit, and rather than on subsequences. And then the most important thing, so if you take sequences like this, which are bounded and therefore have weakly convergent subsequences, and this is a problem because under weak convergence you cannot pass in general to the limit in nonlinear equations, and so you start from the fact that they are converging weakly, but still you are able to prove that the blow-up limit is homogeneous of degree equal to the value of the frequency at 0. Yes, so and for that, and then so this blow-up limit is homogeneous. Okay, so these are not saying much, and then the convergence is strong, well, with the exception of the origin, and the equation which is satisfied by the limit is this one. So Yeah. What should I say about this? Okay. So first of all, homogeneity. So homogeneity will come from looking at these terms under the derivative. So this expression here is integrable. We write how it behaves under rescalings, and then using the lower semi-continuity of the L2 norm. So so when you pass to the limit, and so these are exactly the kind of expressions in the definition of the blow-up sequences. So you still get that for the limit v0 here, and here you get age at 0, and this is the gradient times x or something like that. So it's just same kind of argument we used for homogeneity in the monotonicity formula. So it's a bit more delicate than what people are using to get the homogeneity of blow-ups. Okay. And then, what is the equation satisfied by this v0? So, so our starting point was this kind of equations involving test functions phi, and the characteristic function of the positivity set. So, so you rescale this equation, so you see what is the problem satisfied by the rescaling. So you normalize by dividing by the L2 norm on the boundary, and so all of these characteristic function terms disappear in the blow-up limit, which is due to the fact that v goes to 0. So the so v goes to 0, and v was the ratio between the characteristic function minus 1 divided by, so this is a ratio of two things which both of them go to 0, so the behavior is not clear at all, but we can prove that it goes to 0. So all of these characteristic functions go away from in the limit when you pass to the blow-up limit. So the free boundary being horizontal, it now becomes fully flat in the limit. And then what happens is that v0, the divergence of 1 over x1 gradient of v0 equals 0, but in fact, so in this quarter plane. And v0 is homogeneous, and one can prove that v0 is actually greater than 0 in here. So it's a solution of the same problem where the free boundary condition has been lost completely. And then this leads again to a discussion about Legendre functions. So just like in the identification of blow-up profiles after the monotonicity formula, so this is how we are led to the unique blow-up profile. But it is so there are a lot of details and so on. But so one of the most important issues is how to pass to the limit in the equation under weak convergence. So so the equation was this, which, as you can see, it involves quadratic terms in the gradient of u, and so it always involves quadratic terms even after those rescalings. And if you only have a weak convergence of the gradients, so you cannot pass to the limit in such quadratic terms. So in order to do that, we use some special and deep results of Delors about the concentration compactness of solutions of the Euler equations, which I want to devote a few minutes discussing those. Okay, so so it is here. So we have all of this. So our functions, so the definition of Vm was Vm of x is u of Rx dividing by a constant. So these all correspond to solutions to axisymmetric solution of the 3D Euler equations, and so one way to write this problem, assuming that the free boundary is a curve, is to say that the divergence of 1 over x1 gradient of u, so which is 0 both in the fluid domain but also in the air domain, but however this is discontinuous. Well, the gradient of u is discontinuous at the boundary. So, so if you want to take the free boundary into account, so you can say that this is square root of x2 Hausdorff measure h1 concentrated on the free boundary. So, so this does not occur here. So you could see that more easily in the 2D problem, where the analogous result is delta u is square root of x2, one-dimensional Hausdorff measure on the free boundary. So so delta u is a distribution. So let's say, so you can write it down. You write down the definition of a distribution. So delta u applied to a test function phi is minus integral gradient of u gradient of phi, and then you use integration by parts and Green's formula on both sides of the free boundary, and because there is a jump in the normal derivative of u, so you get this kind of things. So, and then in the 3D problem you have something like this, so which is in the sense of so the divergence is non-negative distribution, and therefore it is radon measure. So in the sense of radon measures. So if we assume that in the air there is a fluid with 0 velocity, so this is a particular example of a vortex sheet. So so there is a jump in the velocity at the interface. So and therefore so the vorticity of the fluid is a measure concentrated on the interface in 3D. So let's see what am I saying on these slides. So so okay, I prefer not to work with the original functions, but regularize them a little bit, and then consider the velocity field in 3 dimensions like this. So these are divergence free, as I said, so not only in the fluid region but in the air and across everything. So this is a global flow, so to say. So it is divergence free globally, and then the vorticity for this function, so which is the curl of the velocity. Normally it would be a vector field, but just like in the 2D, vorticity is a scalar, so here it can also be identified with a scalar function. So So vorticity in axisymmetric flows always points horizontally along these things. And in our problem, so okay, I should have written down the definition of this. So this is this kind of vector here. So so these solutions of the Euler equation have non-negative vorticity. So this is the most important thing. So because they had the vortex sheets had the vorticity of this form. So non-negative measures. If you regularize, you get smooth functions, but with non-negative vorticity. And so the result of the law that we are using is that so if you know that these vorticities are non-negative and bounded in L1, so although you only have weak convergence of the velocity field of this partial derivatives and so on, so you can pass to the limit in this type of quadratic expressions. This is the key point. So if you have a product of two functions, and you know fn converges weakly to f0, gn converges weakly to g0, then if you take fn gn, you can't say about f0 and g0. But if these are velocity fields corresponding to non-negative vorticity, so you can pass to the limit in this type of quadratic combinations of the expression. So in the sense of distributions. So combined with the information from our frequency formula that we have something like this, so we do get actually strong convergence of these blow-up sequences. So yeah, so from weak convergence we do get to strong convergence using these results of the law. And this enables us to pass. So this is the claim about strong convergence. Then this is the equation which is satisfied. So this is non-negative radon measure, and this is a continuous function. So something like this makes sense. And then, so when you are looking for a homogeneous function, solving something like this. And this is how you get the so after an analysis of Legendre functions and so on, so just like before, you get a unique blow-up limit, which is exactly this one. So so this sort of elucidates the behavior at degenerate points. So we use this new scaling suggested like of the natural in view of the frequency formula, and we get a unique limit in this way. So so this is these are the results that I wanted to present about this problem. So there is no point to giving any more details, but finally I would like to spend a few minutes to say what happens in the 2D problem, and what is the effect of vorticity. Because so far in this, so I spent most of the time on the 3D axisymmetric problem, but at the beginning I had I mentioned the 2D problem, and in which it is possible to have vorticity as well. So so 2D problem, first of all, so so let us look at delta u equals 0 and gradient u square equals x2. So first irrotational waves, so to say, and I'm interested in, so singularities occur at points on the horizontal axis. So here the vertical axis does not play any role, And this problem, in fact, can be generalized to n dimensions. So you can actually do it in Rn by replacing x2 with xn. But then it is no longer physical. But it makes sense mathematically, and so it complicates matters somewhat. And then, so in this case, we have a very nice monotonicity formula, which is what you would expect. And then the invariant scaling is has exponent 3/2. And then there are two possible blow-up limits. So this Stokes corner flow with 120 degrees and 0, which is degenerate. Well, in 2D, so to say. So monotonicity formula works in any number of dimensions and gives leads to homogeneity of blow-ups. And then so you do these scalings, and in 2D there are two possibilities. And then in the case when this goes to 0, so degenerate points, the frequency formula works, so which is exactly of this type here, but without these weights. So we first proved the results, of course, for the 2D problem with the monotonicity formula, frequency formula, and only after that we did these 3D things where we see that everything works just as well if we introduce this weight 1 over x1 in various places. And the frequency formula, so the conclusion there is that under certain assumptions, mild and so on, so rules out degenerate points. So under reasonable assumption in the 2D problem, so all singularities are Stokes corner flow. So while here frequency formula enables us to identify some blow profile like this, so in the 2D problem there are no solutions of the right of that equation. So these degenerate points are not possible. Okay, so now when you introduce vorticity, so instead of this you have a semilinear equation. When you try to do monotonicity formula, and it still works, but you don't get a monotone function, but monotone plus perturbation. So these perturbation terms can be controlled and have no effect on the behavior. So homogeneity of blow-ups, it is still true, and in the blow-up limit, vorticity disappears in blow-up. I mean, as you can see, so if you replace u by u of r x over r to the 3/2, then this term, so you pick up some power of r in front of it, so it's killed in the blow-up limit. So in terms of classification of blow-ups is still true. So you get blow-up limits either Stokes corner flow or degenerate points. But now degenerate points are actually possible because this equation has a solution. So if f is a negative constant, let's say with c greater than 0, then u equals minus c over 2 x2 plus square so is a solution of the PD, of the free boundary problem. Yeah, so because if you take a quadratic function, the Laplacian is constant, and for which the free boundary is the real axis. Yes, so the function is 0 on the real axis, and the gradient is also 0 on the real axis. So if you allow vorticity, then this so it's possible to have fully flat solutions. So and therefore these degenerate points cannot be ruled out. But degenerate points can be ruled out if we make a sign assumption on this vorticity at 0. So f of 0, so what should be the sign? So opposite to the one here. So f of 0 should be greater or equal than 0. Then degenerate points are not possible, so we can prove that. And then a frequency formula we are able to prove only in the case of frequency formula only if f of 0 equals 0. So if the vorticity at the free surface is 0. And then, I mean, okay, so in all of these equations and so on, so the formula is nowhere near as nice as we had here, but we have all sorts of additional terms corresponding to this function f, the vorticity, and somehow. Instead of using monotone quantities like we had here all the time, and functions having limits because they are monotone, so what we get there is differential inequalities between the. So we get an inequality between the derivative of the frequency function and the function itself, and so on, and we have to do all sorts of estimates. So which I suppose is also similar to what Professor Garofalo had to, I mean, if the obstacle is not 0 or something, you have some additional terms which you need to try to control. Okay, and this is, yeah, essentially all that I wanted to say. So thank you.
What type of uniqueness you talk about there? Are there any?
So there are no uniqueness for the smooth solutions, you mean? Yeah, so there is no uniqueness result. So this is a.
You got a lot of information in your axis or solution.
So the approach to existence is this bifurcation theory in Banach spaces. So you have a so you are in a Banach space, and you have trivial solutions. So it's like a line of trivial solutions,
Yeah.
and because the problem has certain parameters. So this is lambda, and this is. And the certain value of the parameter, so there is a curve of perturbation of this, and that curve actually can be continued to waves of large amplitude, but it is not known whether it splits into different pieces here or here. So yeah, as the parameter varies, and all of these singular solutions, so singular solutions are, you can say, at the end point of this curve. So yeah, so let's say maybe the the problem is defined in an open set, and this curve approaches the boundary, and this is this kind of singular solutions that I have been studying here with corners. But the open problems are about this smooth solution, so to say, and uniqueness is not known at all.
Yeah, so so this work about the stationary situations, understood. What happens when the situations evolve? Is it very difficult?
It's different community working on that type of problem, and I think, yeah, so nobody has really made the connection. So you can look at the initial value problem for this, and there are well-posedness results like Steve Scholar and a lot of so short time things, and if initial data is small, then you have a global existence as well. But then the I mentioned at some point, so it would be very interesting to see. So if you have these stationary solutions and you perturb them a little bit, so what happens with the, I think that...
Do you have dynamic stability?
Nobody... well, so there are some formal results by applied mathematicians, so to say. So there is this Benjamin Fear instability. I don't know exactly what that is, but it's not rigorous. So no... let's say completely open area. So no...
Do you think that there is, an interest in discussing this issue during the program?
Absolutely.
Dynamic stability of what you do. For instance, this corner, Stokes corners, are they stable?
I don't know. So I would say that there is no rigorous mathematical result. No, this is a big open area, so to say, and maybe a number of people would have some relevant expertise here. But I think this was new for pretty much everybody. So I would definitely like to investigate myself exactly this kind of questions. So what happens when you perturb things and stability and so on? But this is like big project. So definitely would benefit from discussions in the community. But
well, two-dimension case possible, right? 2D case. 3D, of course.
Yeah, no, it's completely well. But even about stationary solution, so in 3D I did the axisymmetric. So there are some results about 3D waves which are doubly periodic. So periodic in two directions, so to say, and without any special geometry. So some papers by Plotnikov and Jos and John Toland also work a little bit. But those are only about very small amplitude solutions. So no theory of 3D steady waves which are not perturbations of flat things. So yeah, 3D is again almost completely open, but everything is much more difficult, and you cannot use these stream functions, so to say. And the free boundary is no longer level set, zero level set of something, and this makes it much more difficult, I would say.
Questions? Okay, so let's thank both speakers this morning.